Good day. As you can see, we're looking at the freezing and boiling point graph, and we want to interpret this and get some good information from it. So I'm going to do some scribbling on here first of all. What we see is the temperature is rising as we add energy, and this energy is likely in the form of heat. And way down here, that's not a 5, that's an S for solid. In the C range, we have a little L for liquid, and up here we have a G for gas. And what happens is, temperature is a measure of kinetic energy, and here we are adding energy, and all of a sudden we don't get a change in kinetic energy. So if we're not changing kinetic energy and we're adding energy, it has to be a change in potential energy. And this is where the change of state is happening. So what we have is we have solid and liquid. And what happens is we end up with this mix of solid and liquid, and we will not get the temperature increasing until all the solid's gone. So once all the solid's gone, then it can start increasing the temperature again. This is why people often put ice in a drink, because as long as ice is there, it's going to take it a lot longer to suddenly get to the point where it can heat up again, or have the temperature go up again, I should say. Now, in this place, for D, we have a liquid and gas, and the same thing. As long as we have some liquid present, the temperature is not going up. Once all liquid's gone, then the temperature can rise some more. If we were cooling, we'd get basically a mirror image reflected horizontally, and we'd come down, plateau, boom, boom, and we'd be back to solid. So it says, what's the freezing point of the substance? So we look for what are called plateaus. Plateau, and we use this word in chemistry, plateaus are where it is flat. Boy, it's hard to write with this. That's supposed to be a U at the end. So the freezing point we can see is 5 degrees. And so we go 5 degrees Celsius. And the boiling point happens to be 15 degrees. Now, because we got plateaus, because it got, that's supposed to be a C, this is terrible. That's 15 degrees Celsius, by the way. Because we got flat parts, it turns out that this is going to be a pure substance. The melting point and the freezing point for a pure substance will be the exact same. So this is going to be 5 degrees. What letter represents the range where the solid is being warmed? And so that is cleverly the little a. What letter represents the range where liquid is being warmed? That's going to be C. And where the vapor is another word for gas, is going to be a little e. What letter represents the melting of the solid? The melting of the solid is here. Solid, liquid, little b. Yikes. And the vaporization of the liquid is going to be D. And allows a change in potential energy. So we want to see the change in potential energy. Well, that's going to be B and D. Since kinetic energy is not changing, potential energy is. Change in kinetic energy will be A. Oh, man. A and C and E. What letter represents condensation? Well, none of these letters really represent condensation. They'd be coming the other way, but we're going to have to go with D. And the same thing, it's going to be B, coming this way. So we're just saying, hey, solid liquid went this way. If we took energy away, we'd get this plateau. If we take this energy away from a gas, we'll eventually hit that plateau. But these plateaus, these flat parts, only occur for a pure substance. If we had a mixture we don't get what's called a point. We don't get a boiling point or a melting point or a freezing point. We get a range. It's not one temperature. But for a pure substance, yikes, for a pure, Jiminy, come on. For a pure substance, that's supposed to be a C. That's about as good as it gets. So for a pure substance, these would be flat. If we had a mixture, we'd have it slightly angled up. The plateaus wouldn't be perfectly flat. They wouldn't be as steep as these other areas. And one last thing we want to say is, this graph is not totally accurate because it takes a lot less energy to melt something than to boil it. And you go back to kinetic molecular theory. To go from solid liquid, we're just jiggling the particles apart. So they don't have to move that far apart. But to go from a liquid to a gas, we have to free up the particles completely and have the particles whipping around. And if we have no container, the energy is going to go in the particles and the particles will actually escape. And you know this from boiling water. The water level goes down as you drive the particles out. So hopefully this sheet will help you with some of the text questions.